One of the major changes to occur in the last decade has been a shift from rear to front-wheel drive. The first front-wheel drive Buick was the 1979 Riviera. The engine was mounted longitudinal and transferred power through a transmission and an external differential mounted in the front of the vehicle. But this design was only used in the Riviera from 1979 to 1985. In 1980, a whole new front-wheel drive system was introduced in the Skylark. This system used a transversely mounted engine and transaxle assembly, and except for the 79 to 85 Riviera, is the front-wheel drive design used in all Buick models to date. Now, even though these two front-wheel drive designs have major differences, they both transfer power to the front wheels in the same manner, using drive axles and constant velocity joints. Drive axles on Buick front-wheel drive vehicles consist of an inner and outer constant velocity joint connected by an axle shaft. On some models, a damper is used to dampen driveline lash. Both the inner and outer joints are completely flexible assemblies. The inner joint also has the capability of axial or in and out movement. Both joints are capable of transferring motion at a constant velocity or speed, regardless of their angle. To help illustrate what constant velocity is, let's build a typical CV joint. The first constant velocity universal joint was the Shepa CV joint. A.H. Shepa designed it in the mid-1920s on a ball and socket principle. The joint fits onto an axle shaft with a splined end. An inner race is splined to the end of the axle shaft. 6 balls are positioned in the grooves of the inner race and are held in position by a cage. An outer race or housing is fitted over this entire assembly. The Shepa joint transfers power between the 2 races through 6 balls. If we draw a line through these balls, we have a plane of contact, which is also known as the plane of constant velocity. True constant velocity occurs when this plane of contact is held constant at 1/2 of the total joint angle. As the joint angles, the balls are always held midway between the 2 shafts, bisecting the angle between them. Therefore, the driven shaft always maintains a constant velocity, no matter what angle is produced between the 2 shafts. In a non-constant velocity joint, such as the traditional Cardan joint, as long as both shafts remain in line, the driven shaft rotates at the same constant speed or velocity as the driving shaft. As soon as the shafts are no longer in line, the plane of contact oscillates back and forth and is alternately perpendicular to the 2 yokes. Due to its geometry, a condition exists which causes the driven shaft to rotate at a speed or velocity that varies during each revolution. This in turn produces pulsations which vary the velocity of the driven shaft. The severity of these pulsations increase as the angle increases and eventually creates a noticeable vibration or surge. Many of you no doubt have experienced this on 4-wheel drive light trucks. When turning sharply and accelerating, you can feel the surging produced by the pulsations. Constant velocity joints effectively solve the surging problem. The Shepa joint is one of 5 different CV joint designs used by Buick. It is used exclusively as an outer joint on all Buick drive axle designs. The 4 remaining joint designs are all used as inner joints. It is the design of this inner joint that is referred to when identifying the drive axle as an assembly. The 4 inner joint designs are the double offset, the cross groove, the tripod, and the S-plan tripod. The double offset design consists of an inner and outer race drivably connected through 6 balls. These balls are located in straight grooves and are positioned and maintained in the constant velocity plane by a cage located between the 2 races. This joint design was first used by Buick in 1980 and was discontinued in 1986. The cross groove joint also consists of an inner and outer race drivably connected through 6 balls. However, these balls are located in helical grooves that are alternately inclined. The balls are positioned and maintained in a constant velocity plane by a cage located between the two races. This joint was introduced in the 1988 Skyhawk, Century, and Skylark. The tripod design CV joint has been used since 1979. This joint consists of a housing drivably connected to a shaft through 3 equally spaced trunnion-mounted balls. There are 2 different variations of the tripod joint. Design A is used in the 79 to 85 Riviera, while Design B is used on all other Buicks. 2 advantages of the tripod design are that it requires low axial force during end movement, and the tripod also operates at cooler temperatures. The S-plan tripod is similar to the tripod design, but has a different trunnion bearing design. The bearing blocks are square and have needle bearings that ride against straight tracks inside the joint housing. This joint performs well at higher operating angles and was introduced in the 1988 Riviera. All CV joints are protected from contamination by a boot seal that is fastened around the joint housing and the axle shaft. The boot seal retains lubrication in the CV joint while still allowing flexibility. Boot seals were originally made of neoprene rubber. Since then, silicone and thermoplastic have been used. Identification of all boot seals is made easy by looking at the color and number of convolutes. The neoprene boot seal has 3 convolutes and is black in color. A silicone boot seal was introduced in the 81 Skylark. It also has 3 convolutes but is gray in color. The silicone boot seal has an advantage over the neoprene boot seal in that it can withstand higher temperatures. A higher temperature grease is also used with the silicone type boot seals. In 1984, thermoplastic boot seals were first used. They are more durable than their silicone and neoprene counterparts. They have 6 convolutes and are also black in color. The thermoplastic material performs well against normal handling and operational wear. However, it is still not strong enough to withstand abusive handling or damage from objects such as sharp tools or the sharp edges of any other surrounding component. In fact, all boot seals should always be protected when working near the drive axle. All of the boot seals are secured to the axle shaft, and most are secured to the joint housing by stainless steel clamps. Some use an eared clamp. Others use an earless clamp. On some early models, the boot seal is secured to the joint housing by a seal retainer. There's a lot of pressure exerted on the inside circumference of the boot seal due to the speed of rotation. The lubricant inside the joint will find its way out through very small holes, so it's imperative that the boot seals are properly clamped during installation. Any damage to the boot seal or clamp results in a loss of lubrication and contamination of the joint. This eventually leads to failure of the internal components of the joint. On some applications, the tripod and S-plan tripod design drive axles use a torsional damper to dampen driveline lash. The damper is part of the right-hand inner joint on 79 to 85 Rivieras. Others have a damper that is part of the right-hand axle shaft. Vehicles that are equipped with anti-lock brake systems have a sensor ring around the outer CV joint. If sensor ring replacement is necessary, the outer constant velocity joint housing must be replaced. Diagnosing drive axle and constant velocity joint problems is done primarily through road tests and visual inspections. The road test verifies the customer's complaint and indicates if there is more than one problem. It also gives something to compare with after the repair has been made to verify that the problem was fixed. 4 common drive axle symptoms are a clicking noise when turning, a clunk when accelerating from coast, a shudder or vibration during acceleration, and a vibration at highway speeds. Using the symptom possible cause chart in the diagnosis section of the reference manual, compare the symptom experienced with the corresponding possible cause. The road test and this chart gives you an idea as to what area of the drive axle could be at fault. Remember, this only indicates a possible cause. Verification of any suspected problem must be done by a thorough visual inspection. Begin by inspecting the entire drive axle assembly. Clamps should be tight and straight. Check boot seals for cuts or damage. The most common cause of CV joint failure is a punctured, pinched, or torn boot seal. The result is a loss of lubrication and contamination of the joint. Often a telltale grease spray can be seen if there is a hole in the boot seal. If a boot seal or clamp is found to be damaged, the CV joint must be inspected for contamination or damage and serviced accordingly. On the 1979 to 1985 Riviera, be sure to inspect the inner flange bolts. Replace them if they are loose or damaged. On all front-wheel drive vehicles, check both joints for play. There should be no noticeable play between the axle shaft and the joint housing. If you can see play, remove the drive axle for overhaul. If a damaged CV joint is suspected, remove the large boot seal clamp using side cutters and pull back on the boot seal. Inspect the joint for dry or damaged components. If found to be dry or contaminated, remove the drive axle. With the drive axle removed, check for joint flexibility. Check the inner joint axial movement. The joint should not bind in any way. With the Shepa and double offset joints, inspect the cage, axle shaft, and housing splines for wear or damage. Inspect all of the balls, race, and housing for rust, pitting, or grooves. A polished appearance is normal and does not indicate a need for replacement. With the tripod and S-plan tripod joints, check that the rollers turn freely without sticking. Inspect the housing for rust, pitting, or grooves. Again, a polished appearance is normal and does not indicate a need for replacement. Inspect the axle shaft and housing splines for wear or damage. The cross-groove joint can be removed from the axle shaft, but is not recommended for disassembly. This joint is serviced by replacement only. On all cars equipped with a damper, inspect it for looseness or damage. Rubber protruding from the end of the damper may indicate internal damage. The damper is an integral part of the axle shaft, and both must be replaced as a unit. The damper cannot be overhauled. An excessive CV joint angle can cause a shudder or vibration during acceleration. This may also be accompanied by a torque steer condition. If an excessive CV joint angle is suspected, measure the distance from the inboard CV joint to the bottom of the frame or lower support. The distance should be equal on both sides. If they are not, check for damaged motor mounts or a bent frame. Next, check the trim height. High trim height can cause excessive CV joint angle. This can cause a shudder condition during acceleration. If all measurements are equal and within specifications, it can be assumed that the joint angles are okay. Be sure to take a good look at the service section of your know-how reference manual. In it, you will find a complete list of special service tools and drive axle removal, installation, and overhaul procedures. Instead of detailing all of these procedures now, let's simply go over some of the important new service procedures and highlight some good general service tips as well. When removing or installing the drive axle assembly, use boot seal protectors whenever possible around the boot seal. This protects the boot seal from damage during service. Some of the bolts and nuts, such as the drive axle hub nut, tie rod end nut, and caliper mounting bolts, may be torque prevailing fasteners. Torque prevailing fasteners incorporate a system to develop an interference between the nut and bolt threads. Interference on this particular drive axle hub nut is achieved by distorting the end of the nut. It is recommended that a new torque prevailing bolt or nut always be used during any reassembly procedure. Use of an alternate hub nut design may compromise the integrity of the fastener's retention qualities. Except for the 79 to 85 Riviera, the drive axle is a press fit into the hub bearing assembly. The use of a hub spindle remover tool is required to separate the spindle from the hub bearing assembly. During removal of the drive axle, some models require separation of the lower ball joint from the steering knuckle. There are 3 different tools used depending on the vehicle. Two of them work similarly by pressing the ball joint stud through the knuckle assembly. The third tool separates the ball joint from the steering knuckle by providing a surface for the ball joint nut to press against. As the nut turns, it pushes the ball joint stud through the knuckle assembly. Removal of the drive axle from the transaxle can sometimes be done by using a pry bar and a wood fulcrum. The wood fulcrum protects the transaxle case from damage. On some models, though, lack of accessibility does not allow the use of a pry bar. In this case, an axle shaft remover, extension, and slide hammer tools must be used to remove the drive axle assembly. Seat the axle shaft remover against the inside of the inner CV joint housing. Remove the drive axle using the slide hammer. When installing a drive axle, seat it into the transaxle using a pry bar and mallet. Place the pry bar in the groove provided on the inner joint. As a final measure, check that the drive axle snap ring has seated in the transaxle assembly by pulling on the inner joint housing. Do not pull on the axle shaft. If the snap ring is seated, only a small amount of axial play can be felt, and the drive axle remains in place. When installing the drive axle hub nut, never use an impact wrench. This can damage the wheel bearing and hub assembly. The basic difference between servicing the S-plan tripod joint and conventional tripod joint is that a metal plate is used during assembly of the S-plan joint. The metal plate is used as an aid to align the square bearing blocks to the tracks in the joint housing. Remove the metal plate after the bearing blocks have started into the tracks. Remember to use caution while handling the S-plan tripod and tripod type CV joints to prevent overextending the joint. Overextension can result in possible disengagement of the bearings from the housing. With the boot seal on, overextension may go undetected during assembly and installation, resulting in separation of internal components, difficult installation, and possible joint failure. Included with each service kit is a special service grease. Be sure to use the proper service grease according to application. They are not interchangeable. Apply half the grease to the internal components of the CV joint and the other half into and on both lips of the boot seal. All boot seals are retained at the small end and most at the large end with the boot seal clamp. Some older models use a seal retainer to secure the boot seal to the CV joint housing. The seal retainer is assembled using an arbor press. Earless clamp pliers are used to secure the earless clamp. Eared clamps are secured using one of two special tools. Keystone clamp pliers are used to secure neoprene and silicone type boot seals. When clamping boot seals made of thermoplastic, the clamping torque is much more critical, and drive axle seal clamp pliers must be used in conjunction with a breaker bar and torque wrench. When the specified torque is achieved, a gap must remain at the crimp of the clamp. When servicing tripod, S-plan tripod, or cross-groove type inner joints equipped with thermoplastic type boot seals, a measurement must be obtained before crimping the large clamp end. Doing so captures the proper amount of air inside the boot seal. This procedure is important because it prevents grease from leaking and the boot seal from collapsing. When working with tripod or S-plan tripod joints, measure from the small end of the boot seal to the specified groove in the CV joint housing. Adjust so that a measurement of 130 millimeters or 5.1 inches is obtained. When working with the cross groove joint, measure from the small end of the boot seal to the groove in the CV joint housing. Adjust so that a measurement of 133 millimeters or 5 1/4 inches is obtained. Finish the job by crimping the large clamp in the same fashion as the small clamp. Incidentally, the drive axle boot seals should be inspected every 7,500 miles. Replace any boot seal that is found to be punctured, pinched, or torn. The 1988 Regal uses a standard tri-pot type drive axle, but is unique in that the drive axle is much more accessible than in previous models. Removal and installation of the drive axle is made through the large hole in the strut knuckle assembly. This eliminates the need to separate the tie rod end and lower ball joint. Remember, for maximum durability and customer satisfaction, always use Buick recommended replacement parts and service kits, and follow the procedures found in the reference manual. Buick drive axles are proven durable assemblies, but they don't often require service. When they do, it's our responsibility to know how to do the job right the first time. That way, our customers can really enjoy the great American road.